All right, what I'd like to do today is walk you through the difference between series and parallel circuits. So let's start with series circuits. Okay, so a series circuit is essentially a very simple circuit. I like to remember these as being connected in a circle. So series is kind of like a circle. Okay. In a series circuit, in any working circuit, remember that we need a potential difference, so a power supply. And then we also have a few resistors. It could be light bulbs, right? Something that's going to use the energy or the potential that is given by that power source. So here's our simple series circuit. I'm going to call my resistor down here R1. I'm going to call this R2. And then up here we'll call this R3. Okay, now remember, in a diagram like this is our schematic diagram of a circuit. The negative side of my battery is that short line, the positive side is the longer line, and we follow the flow of electrons. So electrons are going to leave the negative side, travel through R1, they're going to go through R2, they'll travel through R3, and then finally they will go back to the battery. So you can see that nice simple path, all the electrons go through each resistor. So in a case like this, my total resistance, right, the total resistance that every electron is going to feel is going to be the sum of all of the resistors. So this will be R1 plus R2 plus R3. Okay. The other thing we have to consider is the amount of current that's traveling through here. So the total amount of current that travels through here is going to be the same as the total amount of current that goes through R1, and the same that goes through R2, and the same that goes through R3. So the current through 1 will equal the current through 2 will equal the current through 3. Right? And the reason for that is there's no other path for those electrons to follow. So they have to stay in the same line. They have to all go through each resistor. The last thing here, the last relationship, is the potential difference, or the voltage total, which comes from the battery. Okay? So that essentially is the amount of potential that the current is given. And all of that potential must be used before that current goes back to the battery. So if you look at this diagram, some of this potential will be used in R1, and there'll be some left over. Some more of that potential will be used in R2, and there'll still be some left over. And then the rest of it will be used in R3, so that as this goes from R3 to back to the battery, we say it has no potential, right? So it will have no energy left. So the total potential will be equal to the amount of potential that resistor 1 uses, plus the amount of potential that resistor 2 uses, plus the amount of potential that resistor 3 uses. Okay, so the current has to use all of its energy before it goes back to the battery. Okay. Other things we can add in here are devices to measure these quantities. So we can add an ammeter. Okay, I'm going to put an ammeter here. Right. Notice that the ammeter gets kind of connected right in line with the resistors. So all of the current has to go through that ammeter. So the ammeter is going to read the total amount of current at that location. I could put an ammeter over here. I could put an ammeter up here. Okay. All three of those are going to read the same value because my total current doesn't change as we travel through the circuit. The other thing we can add are voltmeters, right? So I could put a voltmeter around a resistor, right? So voltmeters get connected around a device. So what's going to happen is the voltmeter is going to read how much potential an electron has at this location. That electron is going to go through the resistor, and the voltmeter is going to read how much potential it has at the other location and look at the difference. Okay. One big thing to know about voltmeters is that voltmeters have a huge resistance. Right? So voltmeters have a large resistance. Okay. The reason for that is we don't want electrons to go through the voltmeter. We want the electrons to go through the resistor. Right? So voltmeters have very high resistances so that current doesn't travel through that branch. Okay? Ammeters, on the other hand, right, so my ammeter is here. Ammeters have a very low resistance. And the reason for that is because we want the current to go through it. Right? If ammeters had a large resistance, they would change the total resistance of the circuit, which in turn would change the total current. And that's not the purpose of an ammeter. We just want to read the amount of current that exists. So those are series circuits. Now, things to remember with series circuits, we use Ohm's law a lot, right? So Ohm's law is that relationship between the potential, the current, and the resistance. So you use Ohm's law for the circuit as a whole. So V total equals I total times R total. But you can also use Ohm's law for each individual device, right, or resistor. So V1 equals I1 times R1, or V2 equals I2 times R2, or V3 in this case, since we have 3 resistors, equals I3 times R3. Okay, and so those are series circuits. Now, in a series circuit, if I were to have a break in my circuit, right, if I, for whatever reason, cut this wire right here, if I have a break in the circuit, that is going to cause the entire circuit to stop working. So a break, or this is also known as a short, will cause the entire circuit to stop working. And so if you think of a real world example of something wired in series, where if one light bulb, for instance, goes out, all of the light bulbs go out, hopefully what comes to mind are Christmas lights or strand of holiday lights. Right? Those are a pain in the butt because when one light bulb goes out, usually the whole strand will go out. Right? And that's usually actually in older strands of Christmas lights. Nowadays, they have half of a strand that's wired in series. So if one bulb goes out, about half the strand will go out. Right? Still a pain in the butt, but that's a series. Now let's talk about a parallel circuit. So on the other side here, I'm going to draw some things about parallel circuits. Okay. In a parallel circuit, these are a little bit more complicated. In a parallel circuit, you have multiple paths for current to flow, right? We call these branches. Right? So you have these different branches where current can choose to travel. So let's just draw a parallel circuit, right? So again, I need a potential difference, a power source. And I'm going to have 3 resistors here as well. So here's one. Now, to connect this in parallel, I need to create a whole new path. So if you look at this, current will leave the negative side of my battery and travel in a counterclockwise direction. And it will go up through this resistor. But down here at this point, I'm going to create a junction. So I'm going to add another wire. And then I'm going to add another resistor here. Right? And so what I've done here down here is create a junction. So at that point, current has a choice of where it could go. I'm going to add one more branch here, so I have 3 branches, and then we'll talk about where things are going to go. So I'm going to call this R1, this is R2, and this will be R3. Okay. So let's look at the current. Now I'm going to use 3 different colors to show you how current will travel. Okay. So let's follow, for instance, we'll call this the black current. So it's going to leave the negative side of the battery, right, travel this way. And at this point, I'm going to say that this is going to go through R1. So it's going to travel up through R1, right, and then it will go back to the battery. Okay. My next current, I'm going to use a red color. So my next path of current, right, it's going to leave the battery. I'm going to draw it right next to this. And instead of going through R1, we already had the black line go through R1. This one's going to continue on. So it gets to that point and it's going to keep going. And so when it gets here, it's going to decide to go through R2. And then it will travel, back to the battery. Okay. And then finally, I'm going to have one last flow of current here. I'm going to use blue. So that current will leave the battery. It's not going to go through R1. It's going to keep going. It's not going to go through R2. It's going to keep going. Instead, it's going to go through R3 and then eventually back to the battery. So I like to use 3 different colors. You know what, my diagram kind of got a little crowded, but it shows you how current is going to split and where current is going to meet. So down here, this junction that I circled, right, this is a junction, you have current that is splitting. So here you have all 3 sets of current, black, red, and blue, right, up to this point. And then the black decides to go up, and the red and the blue continue on. Here's another junction. Right? At this point, the red decides to go up through R2, but the blue continues on. And then if you look at the top, we have 2 junctions at the top up here as well. Okay? And so at this first junction, as we're traveling back towards the battery, you have the blue current that's going to meet up with the red current, and then they travel together. They meet at this next junction with the black line, and all 3 of them go back to the battery. So down at the bottom here, you have current that is going to, so I'm going to kind of group these together. You have current that is going to split away from each other. And then up at the top, in these 2 junctions, you have current that is going to join or add together. Okay, so just a good way to kind of analyze what's going on here. So if we think about that, let's first talk about our potential, right? So a certain amount of energy is given to those electrons as they leave the battery. Let's choose to follow the black line first, right? So they're given a certain amount of potential. If we follow the black line, right, we're going up through R1, and that's it. So it's only going through 1 resistor. So that total that it's given, that energy, has to be used as it goes through resistor 1. So V total has to equal V1. Let's follow the path of the red current. So it's given a certain amount of potential. Red current, again, only goes through 1 resistor before it goes back. So the total it's given has to be equal to how much potential it's using in R2. And then same thing with R3. Right, so in a parallel circuit that's set up this way, the total potential that you are given, that those electrons are given, has to equal the potential they use in each branch. Okay, now, we only have 1 resistor in each branch. Right? In more complex circuits, you'll see multiple resistors in a branch, right? And then other things will happen, but the total branch has to equal the potential of the battery, right? That total potential drop of the branch has to equal the total potential of the battery. The next thing to look at is current, right? And so this one is where our colors come into play. So all 3 of these leave as they go through or leave from the battery, and then they split. So the current that leaves the battery has to equal the addition of all 3 of these, right? So we have blue, red, and black that leave the battery, and then if we add all 3 of these branches, we have blue, red, and black, that's going to equal the battery. So I total equals I1 plus I2 plus I3. Okay. And then the last one is our equivalent resistance, right? We don't like to call this the total resistance because you're not adding the resistors here. So this is that weird relationship where you have the inverse. So you have 1 over R1 plus 1 over R2 plus 1 over R3. And that equals 1 over the equivalent resistance, we call it. Okay, so this one's your different piece here. Now, the thing that's special about this is the more branches you add in a parallel circuit, the smaller that resistance becomes, right? The more choices that you're giving those electrons. So I'm going to just write this because this is really important. As more branches are added, in parallel, the total resistance decreases, or that REQ value. Right? This is going to go down. Okay. Again, with a parallel circuit, we use Ohm's law. Right? So you have Ohm's law that's going to apply for the circuit as a whole. So V total equals I total times R total. But here I'm going to use REQ just so you don't get confused. And then you can also use Ohm's law for each branch. So V1 equals I1 times R1, V2 equals I2 times R2, and V3, whoops, these should be I's, right? I1, and this should be I. So I3 times R3. Okay. Now, one last thing about parallel circuits. In a parallel circuit, it makes a difference where you place an ammeter, right? So to place an ammeter in a parallel circuit, so you want to read the whole current, the total current, you want that ammeter to be pretty close to the battery. Okay. You could also place an ammeter in each branch to read the current that's going through each resistor, right? But this is key. Your ammeter you need to place close to the battery in order to read the total amount of current. I total. All right, so it could be as the electrons leave, or it could be on the opposite side, right? I could place it up here, and as the electrons come back into the battery, all of that will go through. Okay. The other thing with a parallel circuit is when you have a break or a short, right, in one of the branches, so let's just say R2 stops working for some reason, right? So if you look at that diagram, the path that the red current decided to travel is not going to work. So the red current will find somewhere else to go, right? So in a parallel circuit, when you have a break, again known as a short, that one branch will stop working. So if that's the case, if that one branch stops working, what happens to the rest of the circuit? It remains working, right? So the rest of the circuit remains working. So if those are light bulbs, then they will stay lit. Okay, so those are your really important relationships with series and parallel circuits. Okay, these are kind of like puzzle pieces. You have to figure out where current is traveling. Is it meeting up? Is it breaking off? Is it the same throughout? Right? You really have to analyze where things are moving. So I highly suggest that you're always drawing the path that the electrons are following, right? And kind of see where things add and where things subtract.